Hello there and Assalamu alaikum. My name is Afif from Group 2B, and me and my friends are going to present about acetone production, about our integrated design project IDP. Alright, then, so let's get into it. Right, so first of all, I'm going to introduce to the principle of chemical engineering that we are using it in this project. Okay, so principles of chemical engineering focuses on fundamental concepts in chemical engineering calculations, which are essential for designing and analyzing industrial processes. A major concept in this field is mass and energy balance. It ensures that what goes into a process equals to what comes out. This allows the laws of conservation of mass and energy, meaning nothing is created or lost, only transformed in the mass or in energy. These principles help engineers optimize processes, reduce waste, and improve efficiency. All right, let's get to the another one. All right, so the second one is the chemical engineering fluid mechanics. The fluid mechanics that we are using in this project. So, chemical engineering fluid mechanics focuses on applying fluid mechanics principles to the design and operation of processes in the chemical industry. This field is essential for understanding and optimizing fluid flow, heat transfer, and mass transfer within chemical engineering systems. It also covers fluid properties like viscosity and density, as well as fluid statics, that means fluids at rest, and fluid dynamics, meaning fluids in motion. One key principle in this subject is Bernoulli's equation, which explains the relationship between pressure, velocity, and height in a flowing fluid. So let's get into uh, the project. Alright then, so now we are seeing the process flow diagram of our acetone plantation. So, in short, is PFD, where we are using isopropanol, aka isopropyl alcohol, to make pure acetone. That's our motive. That's our goal. Alright. So, what is isopropanol? Isopropanol, also known as isopropyl alcohol, is a colorless, volatile, and flammable fluid from the liquid with the chemical formula C3H8O. It is a secondary alcohol, meaning the hydroxyl group of negative OH, meaning the ion, is attached to a carbon that is connected to two other carbon atoms. So let's get to the process. Alright, so there are seven processes in this project, in this plantation. So I'm going to explain to you one by one, and each unit operations, the function of each unit operations in the process. So the first process is the feed preparation unit, where there are three unit operations. So the first one is the feed tank that stores isopropanol at 25 degrees Celsius, 1 atm to ensure a continuous feed, and the second one is pump to transport isopropanol efficiently to the heat exchanger. The third one is check valve one, that prevents backflow of of the IPA, the IPA, as known as you know, isopropanol from the heat exchanger to the pump. Alright, so the second process is preheating and heat exchanger. They are both the same in the heat exchanger. So it has one unit operation, that is the heat exchanger, of course. So the heat exchanger heats IPA from 25 degrees Celsius to 35 degrees Celsius using a heating medium. So the heating medium may be hot oil or uh, steam, and it provides heat input that is 300 to 500 degrees Celsius of heat, and then 280 until 490 of degrees Celsius of output for efficient heat transfer. course. Now let's go to the third one. All right, now we're into the third process and the fourth process of the plantation. So the third process, which is the dehydrogenation reaction, it requires the dehydrogenation reactor, of course, and it converts isopropanol into acetone plus hydrogen gas using a catalyst as we use zinc at 300 to 400 degrees of Celsius, uh, 1 atm pressure. And the chemical reaction, as you see there, uh, from isopropanol, we get acetone plus hydrogen gas. So the fourth process of the blendation is the hydrogen separation from acetone. So from the reactor, after the reaction, the isopropanol will move to the flash separator through the pipe, and then it will be separated there by the flash separator, which removes 90 to 99% of hydrogen gas from acetone using pressure and temperature control. Alright then, so we're now down to the last three. Sorry for the mismatch of the angle. So you just have to bear with me because I need you to see all of them, right? Alright, okay, so the fifth process is the acetone purification and hydrogen recovery. So it consists three operation, that is distillation column that separates acetone from unreacted isopropanol based on boiling points. So you can see there the boiling points. And the second one is the hydrogen recovery tank, which stores pure hydrogen gas recovered from the flash separator and distillation column. Which you can see from the previous slide, the flash separator is going somewhere, and I've written there where it is going, so it should be obvious by now. And you can see the arrows pointing to the tank. The third one is the cooling water tank that supplies cooling water to the condenser for assistant cooling, as you can see there. The sixth process is the unreacted isopropanol recycle stream. So it consists of splitter and check valve tube. So the splitter, sorry, so the splitter diverts unreacted isopropanol back into the recycle stream, reducing waste and improving efficiency. While the check valve tube ensures one-way flow of unreacted isopropanol to the pump. The seventh one is the seventh process is the acetone condensation and storage. So it consists of two more things. As you can see there, it consists of condenser and a pure acetone tank. So the condenser cools hot acetone vapors from the distillation column using cooling water that is 25 degrees of Celsius, producing liquid acetone at 40 degrees of Celsius. So pure acetone tank, obviously, it collects final pure acetone ready for distribution. So I guess that's it. That's all from me. I'm passing it to Hazik. All right.
Hi, I'm Aziz. So today I will talk about mass balance. So from the diagram that is given to us, so I construct the flow diagram. So the purpose of this project is to separate the liquid and the gas product. This is the assumption. The mass flow rate is kilogram. Saturation is hydrogen. Here we exit to the gas channel. So the molar fraction is like the given reaction. So first we need to find the end gas, which is 0.74. How? Because there are only hydrogen gas which in the gas and gas. And then we find the liquid by the equation. So next we can find the we need to find the acetone input first, and then we can find the product in the liquid. This goes same as the isopropanol. So so this is the summary for the whole non-reactive mass balance.
Hi, I am Sarah and I will explain about the energy balance for non-reactive system. As for the non-reactive system, we all choose distillation column, and these are the flow diagram for the distillation column. So these are the assumptions that we'll make. And for the first is the temperature in and out. For the temperature in, we all assume that it is 100 Celsius, and temperature out for the top is 50 degrees Celsius, and also temperature out for the bottom is 80 degrees Celsius. And for the pressure, we assume that in and out is 1 atm, and for the energy equation, for the change of energy kinetic, energy potential, and also the work shaft is all equals to 0. So next step for the calculation for energy balance for non-reactive system is to calculate the specific enthalpies of a substance. So first I calculate the specific enthalpies for the acetone in, which is 100 Celsius, to I make the reference states of its substance, which is acetone is liquid 35 degrees Celsius and 1 atm. For isopropanol, 35 degrees Celsius, 1 atm liquid. And also for hydrogen in gas, 35 degrees Celsius and 1 atm. So I calculate each substance specific enthalpies and get the values. So last step for calculation of energy balance for non-reactive system is I made an inlet outlet enthalpies table, which make it more organized. And for the each component, I get the mole flow rate and also the specific enthalpies for in and out. So calculation for energy balance, we use the equation of energy balance, which I cross out the kinetic potential and also the work shaft as we have in the assumption. So we get the heat transfer equals to the specific heat. So for calculation of heat transfer is mole flow rate times with the specific enthalpies. So I time it out, and the outlet minus with the in of the specific heat. So I get the answer for the heat transfer for energy balance for non-reactive system.
Next, we go to the reactive, which is the how isopropanol is converted into the um, acetone and hydrogen gas. First, we need to find the isopropanol in, and by the percentage excess formula. So, and then we find the acetone out and the hydrogen out, and then we find the mass, and this is the summary for them. That's all from me. Thank you.
Next, I will explain for the energy balance for reactive system. As for the reactive system in the acetone production is the dehydrogenation reactor. As for the dehydrogenation reactor for the energy balance, it is we using a heat of formation for the energy balance. So these are the flow diagram for dehydrogenation process. These are the assumptions for energy balance in reactive system. So first assumption is for the temperature in and out, which I make the temperature in 35 degrees Celsius and temperature out is 100 degrees Celsius. Next assumption is for the pressure, which in and out is equal, which is 1 atm. And last assumption is for the energy equation, uh, change in energy kinetic potential and also the work shaft is equals to 0. So these are the inlet outlets table for specific enthalpies. For the specific enthalpies calculation, I will show it in the next slide. So for the last step of energy balance reactive system calculation is first I calculate the specific enthalpies of each substance. The formula of for reactive system is a bit different as it need additional information. which is the heat of formation of the substance. So, for example, for the first substance is isopropanol in 35 degrees Celsius. So, the heat formation of isopropanol at with the specific enthalpies from the table. It and it's continue with the other substance as we as I got all the specific enthalpies substance. I proceed to calculate the specific heat with which is more forward time with the specific enthalpies of each substance outlet minus inlet, and I get the heat specific heat of energy balance for the system.
Now I'll be presenting about the layout of pipelines. So our layout of pipelines, we have 10 pipelines, and I also inserted two tap valve, which is after the pump and at the recycle stream to prevent the backflow of the products. And if you guys notice, we have inserted red colored numbering, which actually symbolizes where our fittings are, and there are a total of 8 fittings that we use. For this operation, we chose to use 90-degree long radius elbow, which has a smoother 90-degree turn, which makes the K value or the resistance coefficient smaller than 90-degree standard elbow, which can help us to reduce the pressure drop and friction loss. The third one that I would like to emphasize is about the usage of stainless steel in our operation because it is corrosion resistant and have high temperature resistance, which make it very suitable for our operation since most of our reactions undergo with the high temperature. And it also has lower surface roughness, which can lead to less frictional loss too. Now let's start with the calculation for each pipe. For the first pipe, which is isopropanol to heat exchanger, the assumption that we make is steady flow, incompressible fluid. The difference between pressure 1 and pressure 2 is negligible since the pump only increases a small amount of pressure. Velocity U1 equals to U2 since we use the pipe with the same diameter. Z1 equals to Z2, which is same elevation. Density for IPA is 786 kilogram per meter cube. Dynamic viscosity 2.4 times 10 power of negative 3 Pascal second. So for the first step, for us to calculate the uh, power for the pump is we need to calculate the Reynolds number by using the formula rho Vd over dynamic viscosity. How to find the velocity? We need to know the mass flow rate or volumetric flow rate. After calculating, we got the velocity equals to 1.68 meter per second. Now, when we calculate the Reynolds number, we got the value which is 41,925.24, which make our flow is turbulent. Then we can find the relative roughness, which is 2.8 times power of negative 5. Then we need to find the friction factor. For the friction factor, since it is turbulent, we can use Modi's diagram. But to be accurate, I use the formula, and we got 5.36 times the power of negative 3. The next step is we need to make the energy balance equation, and from that we can cancel out the P1, P2, U1, U2, Z1, and Z2, which left us with the work of the pump equals to friction loss. By calculating the friction loss, we can automatically get the work by the pump, which is 12.88 joule per kilogram. The last step is we need to find the power for the pump by multiplying the work by the pump with mass flow rate, and we will get 77.41 joule per second. Moving on to the second part, which is heated IPA to dehydrogenation reactor, the assumption that we made is same as the previous calculation, and we can jump straight away to the energy balance equations since we use the same mass flow rate, the same fluid, which is IPA, and the same Reynolds number, which makes the friction factor same, which is 5.36 times to the power of negative 3. So when we make the energy balance equation, we can cancel out U1, Z1, U2, and Z2, which left us with pressure 1 minus pressure 2, which is pressure drop, equals to friction loss time density. Then we can find the friction loss by using the formula. And for this pipe, the length of the pipe is 20 meter. Actually, then we will get the friction loss 10.06 joule per kilogram. By multiplying the friction loss with the density, which is 786, we can get the pressure drop for this pipe, which is 7,907.16 Pascal. For the third pipe, which is from the dehydrogenation reactor to flash separator, we have three components in this stream, which is the excess IPA, acetone, and hydrogen gas. For the assumption, we make the same assumption as previous calculation, but for velocity and Reynolds number, we use the one with the highest composition, which is acetone. But for the hydrogen, we neglected it. The calculation step just same as before, which we need to find the Reynolds number. For this flow, we got it turbulent with 286,031.71. Then we need to find the relative roughness, 2.8 times 10 to the power of negative 5. Actually, it is the same as before since we use the same type of pipe, which is 3-inch diameter stainless steel. And then using the Moody's diagram or the formula, we can get the friction factor 3.57 times the power of negative 3. Then for the last step, we need to find the pressure drop by using the energy balance equation, where we can cancel out the U1, U2, Z1, and Z2. Will leave us with P1 minus P2 equals to friction factor, friction loss time density. Then we will get the pressure drop of 5,135.66 Pascal. For the first stream, which is hydrogen out from flash separated to hydrogen storage tank, it is full of hydrogen gas, so it is basically compressible fluid. The assumption that we make is adiabatic flow with friction loss. The Mach number for the outlet is equals to 1, which is critical state as the mass flow rate doesn't change. Temperature 1 equals to 293.15 Kelvin. R for hydrogen equals to 4124.2 joule per mole Kelvin. K equals to 1.4. So for the calculation step, the first step is we need to find the Mach number for the entrance, which is Mach equals to V over C. But we don't have the value for the velocity, so we need to find it first by using the mass flow rate that we got. Then our velocity is 512.54 meter per second. Then we need to find the P1 since we will be using the formula which show the relationship between the pressure and the Mach number. Then P1 is a very needed value. We can calculate P1 equals to rho RT by using the ideal gas equation, and our P1 is 100,347.75 Pascal. Then after we substitute all the value in the equation that we will use, our P2 value is 36265.09 Pascal, which made our pressure drop is 64,082.66 Pascal. For the fifth stream, which is acetone feed to distillation column, basically in this stream we also have three components, which is acetone, excess IPA, and hydrogen. But the calculation is as same as the previous in the third stream, and also the assumptions. So I will skip about that. Then the density for acetone is 784. Then we need to calculate the Reynolds number, the relative roughness, the friction factor. Then we will do the energy balance equations, which leave us with pressure drop equals to friction loss time density. The friction loss that we will get is 6.4679 joule per kilogram. And the length for the pipe is 20 meter. So for the pressure drop, multiplying the friction factor with the density 784, then we will get 5070.86 Pascal. Next, for the hydrogen out from distillation column to recovery tank, it is same as the first stream, which it is full of hydrogen and basically is compressible fluid. So the assumption is same as before. The first step, we need to find the Mach number for the entrance by using the formula V over C. As usual, we need to find the velocity first, and the velocity is 459.697 meter per second. Then for the Mach number, we get 0.35. Next, we need to find the pressure 1, which is 100,347.77 Pascal. Then we will substitute all the value that we got in the formula, which show the equation between the pressure and the Mach number. Then we will get the P2 value, which is 19,790.08 Pascal. For the pressure drop, P1 minus P2, then we will get 18,557.69 Pascal. Next, for the seventh pipe, which is liquid product from distillation to splitter, it is incompressible fluid, and the assumption is same as before, but we make Z1 equals to 0, which is our datum, and Z2 equals to negative 20 meter. And I will provide you can look at the diagram before. For the mass flow rate that we get from the principal chemical engineering part, which is 5.826 kilogram per second. Then from that, we can find the velocity, which is 1.63 meter per second. And as usual, we will find the Reynolds number. And for this stream, it is turbulent. Then we will find the friction, the relative roughness. Then after that, we will find the friction factor, which is 3.59 10 to the power of negative 3. Next, we will do the energy balance equation. When we cancel out the U1, U2, and Z1, we will get P1 minus P2 equals to F times density plus density times gravity times Z2. So substitute all the value, but first we need to find the friction loss, which we will get 12.62 joule per kg. After we get the friction loss, just substitute in the formula just now. Then we will get our pressure drop, which is negative 143,926.72 Pascal. Moving on to the next stream, which is acetone from splitter to condenser. And actually, it will also be the same for the next one, which is condensed acetone to product tank. The assumption that we make is also same as previous, since it is incompressible fluid and steady flow. The U1 equals to U2 and Z1 equals to Z2. Also, for the calculation, it's also same. For the mass flow rate acetone, which is we got from the mass balance, we get 5.631 kilogram per second. Then we can find the velocity, which is 1.57 meter per second. And we can use the value to calculate the Reynolds number, which we will get a turbulent flow. Then we can get the friction factor, which is 3.57 times to the power of negative 3. As usual, we will do the energy balance equation. P1 over rho g plus u1 square over 2g plus z1 equals to p2 over rho g plus u2 square over 2g plus z1 plus f over g. After we cancel out all the things that are same, u1, u2, z1, z2, we will get p1 minus p2 equals to friction loss time density. Then we will get the friction loss is 6.47 joule per kg, and our pressure drop is 5070.86 Pascal. Now for the last stream, which is unreacted isopropanol through recycled stream. So the assumption is it is steady flow, incompressible fluid, U1 equals to U2, Z1 equals to 0, our datum, and Z2 equals to 100 meter. So for this one, our mass flow rate for IPA is 0.194 kilogram per second. The dynamic viscosity for IPA is 2.4 times 10 to the power of negative 3 Pascal second, and our density is 786 kilogram per meter cube. Then as usual, we will find the Reynolds number first, but we need the velocity value. Then we find the velocity by using the mass flow rate that we got, which is 0.054 meter per second. Then we will calculate the Reynolds number, and when we calculate it, we get 1347.6, which is it is less than 2000, which make our flow is actually laminar. So for laminar flow, we need to find the friction factor using the formula 16 over Reynolds number. Then we will get 0.0119. Then we need to find the friction loss, which is 0.34 joule per kilogram. As usual, do the energy balance equation, where we will get P1 minus P2 equals to rho GZ2 plus rho F. Substitute all the value, then we will get the pressure drop, which is 771,333.24 Pascal.
Hello, my name is Johan Raslan, and now I will be telling you about the description of the pipe. The delivery system for transferring isopropyl alcohol from the distillation column to the bottom storage tank is intended to provide efficient flow, minimal pressure drop, and safety compliance. The pipeline and its components are organized as follows. So our first point is the pipe material. The material of our pipeline is stainless steel. and it's selected because of its resistance to corrosion and its appropriateness for managing isopropyl alcohol. Next up we have is our pipe diameter. The pipeline features a diameter of 0.0762 meters, which is converted to 3 inches, to maintain an ideal flow rate and minimize pressure drop. Moving on, we have our pipe length. The total length of the entire pipeline is 100 meters, which allows for an efficient transport from the distillation column to the storage tank. Moving on, we have our fittings and valves. A globe valve is utilized for precise flow control, while expansion joints and a 90-degree elbow fittings are used to handle direction changes. Next up, we have our pressure drop consideration. The pipeline is designed to reduce pressure losses by limiting sudden diameter changes and excessive fittings. Last but not least, we have our surface roughness. The stainless steel pipeline has a surface roughness factor of 0.002 millimeters, which results in a smooth fluid conveyance. Now, I will move on to the transfer mechanism and equipment. To guarantee a seamless transition of isopropyl alcohol from the distillation column to the storage tank, the following steps are taken. Step 1 is pump assistance. A centrifugal pump is employed to supply the pressure required for isopropyl alcohol movement, ensuring a consistent flow rate despite elevation variations. The second step is pressure regulation. Pressure relief valves are installed in the pipeline to maintain safe operating limits and prevent leaks. The third step is flow optimization. The system includes minimal fittings to reduce turbulence and friction losses, improving the efficiency. Last but not least, we have our storage tank specifications, whereby the material is stainless steel with a capacity of 20,000 meter cubes. The internal diameter is 60 meters with a wall thickness of zero point 0.6 meters, and the inlet connection is sealed to prevent contaminations and as well as vapor loss. We have now reached the conclusions of our integrated design projects. Overall, the project focused on industrial scale manufacturing of isopropyl alcohol, which integrated the principles of chemical engineering as well as the fluid mechanic principles to ensure efficiency, safety, and sustainability. We developed a detailed process flow diagram that outlined both reactive and non-reactive processes. Through mass and energy balance calculations, we optimized material movement, heat exchange, and overall process efficiency, minimizing waste and improving cost effectiveness. In a fluid mechanics standpoint, we designed an optimized pipeline system to maintain ideal flow rates and minimize pressure losses. Careful selection of the pipe materials, sizes, as well as the fittings ensured operational stability and compliance with industry standards. The transfer mechanism for the distillation column to the storage tank was another key focus, and so we incorporated items such as centrifugal pumps, pressure relief valves, and flow control devices to guarantee a smooth and controlled transfer process, whilst considering pipe resistance, fitting losses, and power pump requirements. Additionally, we designed a large stainless steel storage tank with structural integrity, corrosion resistance, and safety features to prevent contamination and vapor loss. Overall, this project provides a comprehensive approach to designing and optimizing an industrial isopropyl alcohol manufacturing plant. With the integration of the principles of chemical engineering as well as the chemical engineering fluid mechanics, conducting thorough calculations, and selecting appropriate equipment, we present a practical, implementable solution that enhances the efficiency and as well as the sustainability. That is all from our group. Thank you very much.